Digital is small.
Digital is fast.
Thomas Jefferson, under whom John Marshall served.
Digital
Thomas Jefferson
converges
was a Democratic
diverse
Republican
media.
who defeated the Federalists in the election of 1801.
Digital is the order of the day.
Our vision, imagination, and creations are being increasingly shaped by digital technology.
In digital technology, the media records the data only. It has nothing to do with the information. In analog technology, we actually record the information itself. If we paint a tiger, the information itself is being recorded and everyone will be able to make out how does the tiger look like. But in case of digital technology, we give some data like TIGER, tiger. If the person is not familiar with the word, like a Spanish person who doesn't know English, tiger doesn't mean anything to him.
In digital recording, the analog signal of video or sound is converted into a stream of discrete numbers. In case of an audio signal, these numbers represent changes in air pressure through time. Thus, an abstract template for the original sound is created. The analog signal is transmitted from the input device to an analog to digital converter. The analog to digital converter converts this signal to a series of binary digits.
The number of digits produced in 1 second is called the sample rate.
These numbers are stored onto a recording medium.
This medium may be a magnetic tape or hard drive or optical drive.
The sequence of numbers is transmitted from storage into a digital to analog converter, which converts the numbers back to an analog signal. This signal is amplified and transmitted to the loudspeakers or video screen. In the history of digitization, the technology of digitizing images developed hand in hand with sound. Arguably, digital image processing began at the Jet Propulsion Laboratory in California in the 1960s.
In 1957, Max Matthews of Bell Laboratories developed the process to digitally record sound via a computer. He wrote a program called Music that was later widely used for sound generation.
Computer synthesis of sound started in the United States in the late 1950s, and at that time computers were so weak by comparison to today's computers that it took many seconds to make a second of sound. So you couldn't play a computer in real time like you play a violin. There just couldn't go that fast.
Matthews wrote, "The timbers and notes were not inspiring, but the technical breakthrough is still reverberating."
For the rest of the century, he continued as a leader in digital audio research, synthesizing music and human-computer interaction as it pertains to music performance.
How can the performer control all these many instrument sounds? And the model that I'm using for this control is not the model of a violinist or pianist playing a score. Rather, it's the model of an orchestra conductor conducting music. The orchestra conductor doesn't have to play all the notes in the piece, or any of the notes, but he can control the expression of the piece and get the musicians to follow his batons.
In 1970, James Russell patented the first digital-to-optical recording and playback system. Russell's design was later adopted for developing the compact disc.
Russell was an avid music listener. Like many audiophiles of the time, he was frustrated by the wear and tear suffered by his vinyl phonograph records. Alone at home on a Saturday afternoon, Russell was inspired by a truly revolutionary idea. He began to sketch out a very different music recording system, one in which there would be no physical contact between the disc and the stylus. In Russell's design, the stylus was replaced by a razor-sharp laser beam.
In 1979, at the heart of digital technology lies binary arithmetic, where all the numbers are expressed in terms of only two digits, 0 and 1. In the commonly used decimal system, the value of a number is determined in the following way. The digit 5 is in the hundreds place, the digit 3 is in the tens place, and the digit 7 in the units place.
Therefore, the value of the number is 500 plus 30 plus 7, that is 537.
Now, applying the same logic, let us try to find the value of the number 1, 1 in the binary system. The 1 to the right is in the units place, so its place value is determined by 1 multiplied by 2 to the power 0. The 1 to the left is in the tens place, so its place value is determined by 1 multiplied by 2 to the power 1. Thus we have 2 plus 1 equal to 3.
So 1 1 is 3 and not 11.
Let us see how much will be 1 0 0. We apply the same logic and the value turns out to be 4.
Each 0 or 1 is called a bit. 8 bits make a byte.
However, the highest value that can be represented in an 8-bit byte is only 255. Let us see how. Therefore, in order to represent higher numbers, one can use 16 bits.
Or 32 bits.
So this 16-bit byte represents 1 multiplied by 2 to the power 15 plus 1 multiplied by 2 to the power 1.
Finally we have got it. 32,768 plus 2. That makes it 32,770.
And this 32-bit byte represents 2,147,483,650.
If you have the time and inclination, you can figure out the highest numbers represented by this 16-bit byte.
And the 32-bit byte. Analog signals are continuously variable both in numbers of possible values of the signal at a given time, as well as in the number of points in the signal in a given period of time. However, a digital signal is discrete in both these respects. Therefore, digitization in practical terms can only be an approximation of the signal it represents. Digitization is the representation of an object, image, sound, or document or a signal by a discrete set of its points. The result is the digital image of the object.
The first stage in the process of digitization is sampling. The signal is broken up into tiny segments. The second stage is quantization, where an average rounded off value is assigned to each sample. After sampling and quantization, a smoothly undulating sound signal will take on a stepped look.
If the sampling is done minutely, the steps will be smaller and the quantized signal will more closely resemble the original analog signal. The minuteness of sampling is measured by the sampling frequency. The quantization is done either by truncating or rounding off. When rounded off, 5.3 becomes 5 and 5.7 becomes 6. When truncated, both 5.3 and 5.7 become 5. Each quantized step is represented as bits, that is, a series of zeros and ones. The step with a value 7 will be 111 and the step or quantum with a value 8 will be 1000.
The bits are recorded as a series of hills and dales. The hill represents a 1, that is, the existence of a signal. The dale represents a 0, that is, the absence of a signal.
A series of bits representing one quantum of the signal is called a byte or word. The word size may be standardized to 16 bits or 32 bits or higher values.
Thus, the original analog signal is digitized to a long chain of hills and dales.
To record a stereophonic audio signal at 44.1 kHz sample rate with a 16-bit word size, the recording software has to handle 14,11,200 bits per second.
In analog technology, we get the actual sound, or I would say we get the reproduction of the actual sound. In digital technology, we can go very close to the actual or original sound, but we cannot achieve the original one. There are many factors, and and whenever you are in digital domain, you are going by approximation theory.
The quantization and requantization of digital data yields error. If this repetitive error is correlated to the signal, it results in a cyclical, mathematically determinable error. The human ear functions much like a Fourier transform, and it can detect individual frequencies. The ear is therefore very sensitive to distortion or additional frequency content that colors the sound differently, but far less sensitive to random noise at all frequencies.
Let us zoom into two consecutive troughs of this digitized wave. A sensitive ear can pick up the repetitive patterns of distortion.
To overcome this problem, the concept of dither has been introduced. When a random noise is added as a dither, the waveforms smoothen out. Now the distortion does not follow any predictable pattern. Dither is an intentionally applied form of noise used to randomize quantization error. This prevents a patterned noise appearing in the digitally recorded signal. Needless to say, dither becomes more useful when the word size or the number of bits used to represent the samples is low.
A 16-bit 500 Hz signal sounds like this. When the same signal is recorded as a 6-bit signal, distortions appear as harmonics. But the distortions can be randomized and reduced by applying dither.
Recording with a 24-bit byte is considered an optimum word length. This allows a signal-to-noise ratio exceeding that of most analog circuitry.
By necessity, analog circuitry must be used in at least 2 points in the recording playback chain.
Besides dither, the other correctional aspect required in digitizing any data is aliasing. Aliasing refers to an effect that causes different signals to become indistinguishable when sampled. It also refers to the distortion that occurs when a signal reconstructed from the samples is different from the original continuous signal.
The Times New Roman A is a case in point, but at least the digitized A is recognizable as an A.
Watch what happens when two sine waves of widely different frequencies are sampled and quantized. The wave with a lower frequency loses its smoothness, but still it retains its ups and downs. The high frequency wave simply gets reduced to a square wave, retaining only its highest and the lowest point.
Create a set of sound signals of different frequencies. Now subject these signals to sampling of different frequencies from 100 samples a second to 10,000 samples a second.
Observe carefully what happens. The sound signals of high frequencies become unrecognizable when subjected to low sampling frequencies. To overcome aliasing, the sound signal must be sampled at a rate at least twice that of the highest frequency component in the signal. This is known as the Nyquist-Shannon sampling theorem. For all professional digital recording, the sampling frequency is 44.1 kHz. For high-quality digital recording, sampling frequency is 96 kHz.
Quality of sound depends on the number of samples or number of data and the algorithm of the software. If the number of data gets increased or the algorithm is good enough to recreate the audio signal with the help of the given data, then the sound will be good enough for listening. But if one of these two parameters, like the number of data and the algorithm, are not good enough to recreate the sound, the audio signal will not be able to reproduce properly. So, audio depends on number of data and the algorithm. It has nothing to do with media. But in case of analog technology, media takes a great role.
A quick recap before we proceed.
The process of digitization begins with sampling. An analog signal is sampled into tiny portions.
The next step is quantization. Each portion is quantized to a whole number value.
This whole number is represented in terms of zeros and ones using binary arithmetic.
The repetitive patterns of distortion introduced by quantization are smoothed out by introducing a random noise called dither.
In order to prevent aliasing, the sampling frequency is kept at least double that of highest frequency present in the signal.
This digital recording is always an approximation. In spite of these approximations, why is a digital sound considered noise-free?
The reason is that even if the hills and dales representing the bits get distorted in shape at one stage in the audio chain, at the next stage they are restored back to their original shape. For the same reason, there is very little generation loss in the digital transfer or re-recording of sound or any other data.
However, the discerning ear, used to listening to analog sound, is not always completely comfortable with digital sound. He may find it a bit grainy or sometimes too clean to be realistic.
There are many advantages or many features in digital technology, I would say, which are not there or which are very difficult to incorporate in analog machine. One is like flexibility of the machine. Second is the cost effectiveness of the machine. Digital machines are very cheap in comparison to the analog machine. And the flexibility, suppose in analog domain, if you want to change my pitch, suppose my pitch is too high, it's shrilling, it's very sharp, you want to make my voice little bassy, what you need to do, you need to run the tape in a lower speed. But if you run the tape in a lower speed, what will happen, the tempo will be changed or the pace will be changed.
But if you run the tape in a lower speed, what will happen? The tempo will be changed or the pace will be changed.
In digital technology, that problems can be overcome. You just change the pitch, your tempo will remain same, or you change the tempo, your pitch will remain same.
You just change the pitch, your tempo will remain same, or you change the tempo, your pitch will remain same.
You just change the pitch, your tempo will remain same, or you change the tempo, your pitch will remain same. These are the flexibilities which are there in the digital machine, and to incorporate these features in the analog machine is very difficult and very expensive. It becomes very expensive. Another example, like suppose you have two machines, video machine and an audio machine. Your picture will come from the video recorder, your audio will come from the audio recorder. Now you need to synchronize between these two. Now synchronizing these two machines in digital domain is very easy and very cheap as well. But synchronizing these two machines in analog domain is very expensive. So the question is of expense and flexibility, which is making the digital domain a popular format for the common people or as well as for the professionals also.
The advantages of digital technology far outweigh the minor discomforts of graininess and repetitive patterns of distortion.
Digital technology has not only revolutionized the recording and playback process, it has revolutionized the aesthetics and the thinking process of composers and musicians.